Hello everyone. So far we have looked at solving this particular image classification problem by considering specific set of hyperparameters during the model training process. So all of these hyperparameters generally had some fixed constant values. Like we have considered a value of 0.001 for learning rate. We have considered batch size to have a value of 128 and all. So specifically when we have created the data loader objects, we only have considered a batch size of 128 which was fixed in nature. So we essentially have also looked at considering other hyperparameters to have fixed values like the number of neurons that we can define within the hidden layer, so on and so forth. I don't want to get into all of these details, like what are the different hyperparameters and what are the different values that we have considered for our previous model training process. But what I would want to stress upon here is to conduct the hyperparameter tuning. So conducting hyperparameter tuning is one of the critical steps in model building process. So we cannot simply go about considering some arbitrary values for different hyperparameters and then create a model. We need to evaluate all possible combination of hyperparameters and try and identify which of those combinations is going to result in a model that performs better. Not only provides good accuracy, but it also provides consistent results on validation set as well as test set. Speaking about validation and test sets, we initially have partitioned our data. We have partitioned our data into train set, the validation set as well as test set. We had equivalent number of observations for both validation set as well as test set during the data partitioning exercise. Okay. So we thought about considering the validation set purely for hyperparameter tuning purposes. So we consider this validation set only to evaluate which of these hyperparameters is going to result in a good performing model. And we thought about leaving the test set completely as unseen data, so we get a true unbiased estimate out of it. Whether the accuracy that we obtain over the test set, whether it's close enough to the validation accuracy that we have obtained for a given hyperparameter that we have finalized. That's the whole exercise that we plan to conduct. Now, let us first define the hyperparameter grid and implement the whole hyperparameter tuning process. So let me define a new dictionary called hyperparam grid, which considers different hyperparameters that we are planning to tune. The very first hyperparameter that I'm considering is learning rate, wherein I'm providing some possible values here, like 0.001, 0.0001, and e to the power of -5, some arbitrary values. I'm also providing batch size here. So the possible values for batch size could be 32, 64, 128, so on and so forth. I'm only considering two different hyperparameters for simplicity. You can expand this hyperparameter grid to any possible number of hyperparameters that you would want to fine tune within your model training process. Also provide a possible range of values for the respective hyperparameter that you are considering, just like what we have done for learning rate and batch size here. So hyperparameter grid dot items is going to result in key value pairs to me. So I would want to unpack this items of this particular dictionary into keys and values. So star here is the unpacking operator. I just wanted to zip the items so that we extract keys and values accordingly. So keys and values are nothing but the keys of this particular dictionary, which are nothing but the learning rate and batch size. Values here are nothing but the list objects. So the first list object is associated with the learning rate, the list of possible values that we need to search for learning rate. The second list object here is going to be the possible values that we need to search for batch size here. So this is associated with batch size now. So once we have extracted all of these values, so we want to actually find the Cartesian product of all these hyperparameters as stated above. Right? So how do I find the Cartesian? Cartesian product is nothing but finding all possible combinations. The first combination here could be for the first value of learning rate, we take the first possible value within batch size. So this is one combination. So 0.001, 64, this is second combination. 0.001, 128, this is third combination. So once all of these are exhausted, you pick up the subsequent value within learning rate, that is e to the power of -4, e to the power of -4, 32, e to the power of -4, 64, and then with 128. So you just try to construct all possible combinations of this hyperparameter grid, which is nothing but the Cartesian product here. So here I am going to consider whatever values that I have obtained in the previous step. And now I'm going to make use of itertools.product, which is going to result in the Cartesian product that we are looking for. So I would import the itertools first, itertools module. And then for every possible value that I read, so I just write simple list comprehension, V for V in, that's all. So V for V in itertools.product, within the parentheses, I write values here. So star here is unpacking operator, as you already know. And while presenting the values to the user, so while I present these values to the user, I also would want to combine these individual tuple values that I'm observing with keys as well. So I would zip the different keys that are available and the values that are available. Okay, because so this corresponds to LR and this value corresponds to batch size here. That's why I would want to zip both keys and values that I'm observing for every product within the Cartesian product that we have derived. So now I would wrap this as a dictionary. So I'm storing the result in a list object as different dictionary objects. So for every possible combination of hyperparameters that are derived from the hyperparameter grid are now stored in the form of dictionary objects. So I'm going to make use of this particular list called params in performing my model training process. So I'm going to make use of this particular list object in my model training process. Speaking about the model training process, I'm going to consider this whole code that we already have written. I'll paste it here. Now I'm going to write an outer for loop for param in params that we have determined in the previous step. For each of these parameter combination, I'm going to conduct this model training process now. But instead of providing some fixed and constant values for learning rate and batch size, I would infer the batch size and learning rate values from the individual dictionaries within this inner for loop. Okay, so let me consider recreating the data loader objects that we already have created. So we navigate to this particular step, copy this whole code, and then recreate all these data loader objects, train, validation, and test loader. But instead of providing this arbitrary value of 128, now I actually provide this particular, or I actually provide a reference to this batch size pertinent to this particular dictionary that we are actually reading from the possible combinations of the parameters from this given list. So I'll replace this 128 with the reference to batch size in the given dictionary. So this is the dictionary that I am currently on in the first iteration, right? So instead of hard coding the value as 32, now I am referencing the value by providing the key within this subscript notation, the key of that particular dictionary within the subscript notation. I would also want to update the data loader objects since I'm now pointing to GPU here. So custom data loader is a class basically which pushes all of your batches of X and Y data onto a specific device being GPU, as we already have defined it in one of our previous steps. So once all the relevant data loader objects are defined, now is the time that we go about creating the model object, push that particular model object onto the GPU device. Along with that, we also define the loss function as well as the optimizer object. And then instead of computing the validation accuracy and test accuracy at the end of each epoch, now I would want to compute validation and test accuracies at the end of each parameter combination evaluation. Okay. So along with validation accuracy and test accuracy, I would want to compute what the train accuracy is by providing train data loader object within the parenthesis as an argument while you invoke this function called evaluate. So I would also try to keep track of the accuracy obtained on train set within this particular result data frame here. At the end of the whole process, I would define the column names. So I also would want to include the dictionary of parameters as such so that I would understand what are the corresponding learning rate and batch size values for the different evaluation metrics that we have tracked. Okay. So I'm providing the column names in this particular step here. The first column name is going to be the parameter dictionary. Here it's going to be the epoch, the maximum epoch value that we have obtained so far. And then train accuracy, followed by validation and test accuracy as well. So instead of providing the number of epochs as 50, I would provide the number of epochs to be just 2. So this is just to reduce the overall runtime. For a better explanation to you, I am reducing the number of epochs from 50 to 2. But I would strongly encourage you to have the number of epochs as an arbitrarily higher value like 100 or 200 or 500, and then implement early stopping criteria. So I would ask you to implement early stopping within this particular block of code. Implement early stopping by providing an epoch value to be probably 500 or 1000. It really doesn't matter, because if the validation accuracy is not improving in your iterations that you are conducting, or in your epochs that you are conducting, to be more precise, if it's not improving, then you are going to end the training process then and there. You're not going to conduct the remaining epochs at all. I would strongly encourage you to incorporate or retrofit this particular code to implement the early stopping, as well as update this number of epochs that I'm providing here as 2 to 500 or 1000. Okay. So let me run this whole process. Let me run this whole code. And this is a progress bar that we are showing. It's clearly stating that there are only 2 epochs that it's conducting for every parameter that we are trying to evaluate. For every parameter, we're now going to conduct only 2 epochs. So once this is done, so there are 9 combinations in total. There will be 9 progress bars that will be shown now. So once this whole training process is done, I would want to arrange this particular data frame. I would want to sort this particular data frame by the validation accuracy arranged in descending order. So ascending is equal to false here. All what I'm trying to do here is I'm just trying to identify which of these parameter combinations resulted in a lesser deviation between train and validation accuracies. At the same time, whatever accuracy that I have obtained on test set, whether it's close enough to validation accuracy or not. So that's the expectation. So whatever test accuracy that you obtain, we expect it to be pretty much similar to the validation accuracy. At the same time, we also would want to see the deviation between train and validation accuracy, so as to understand whatever model that we have created, whether it's generalized in nature or not. So all what we are trying to do here is we are trying to create a model object which is much more generalized in nature. Along with that, we are also trying to understand that the model does not have any overfitting or underfitting by validating the unseen data or test data accuracy, comparing it with validation accuracy. Okay. So we finalize one such hyperparameter combination that's going to provide us a very high validation accuracy and a minimal deviation between train and validation. And we also would want to do an additional check on the resultant unseen test accuracy, whether it's close enough to validation accuracy or not. So this is a whole exercise that I would want to strongly encourage you to conduct. Okay. I'm leaving this as an exercise since this is going to take a pretty good amount of runtime. And finally, I would want you to inspect how the results would come out. Okay. So that's pretty much all I wanted to discuss with you in this session. Thanks for watching.